Hello everyone, my name is Rıdvan. I am a freshman mechanical engineering student at Bilkent University. In this video, I'm going to introduce my Physics 101 lab project where I determined the spring constant and the damping coefficient of a vertical spring mass system. The aim of this experiment was to analyze both simple harmonic motion and damped harmonic motion by collecting real measurements and comparing them with theoretical predictions. In this experiment, I focused on determining two important physical quantities. The first one is the spring constant, which measures how stiff the spring is, and the second one is damping coefficient, which tells us how quickly the oscillations lose their energy over time. And also I used graphical method to obtain both of these values. For the first part of my experiment, I used a metal spring, a set of masses, a ruler, a stand to hold the spring, and a stopwatch. With this simple setup, I was able to measure oscillation periods. First, I taped a ruler to my stand so I could see the peaks more easily. Then I placed the spring on the stand and hung different masses on it. For each mass, I pulled the mass down by 1 or 2 cm and released it. I measured the time for 10 complete oscillations using a stopwatch, and I divided this by 10 to find the period t. Then I calculated t square. To get a more accurate period time, I measured the period for each mass 3 times, and then I took the average of these measured periods. I collect my measurements on a table. I plot t square versus the mass in kilograms. The theoretical model predicts a linear relationship, and my graph confirmed this. The slope of my graph was approximately 5.776 seconds square per kilogram. I calculated the spring constant by using these equations from Giancoli 2005 as 6.835 Newton per meters. For the damping part, I continued to use the same system, but I changed my spring and I attached a pointer to my mass to make it easier to determine peak points. I recorded how the amplitude of the oscillations decreased over time by using a slow motion camera. I measured the peak points, converted them to meters, and calculated their natural logarithms. After calculations, I collected my data in a table. Then I plotted ln versus time. The slope of this graph was minus 0.0133. According to the damping equation from Halliday et al. 2014, I found the damping coefficient as approximately 0.00266 kg per second. This shows the system is very weakly damped, mostly due to air resistance and internal friction in the spring. Finally, although the data and graphs I obtained were fairly consistent, there were some errors. And the main sources of these errors are reaction time when using stopwatch, small differences in initial release amplitude, difficulty reading peak positions on the ruler, and slight non-ideal behavior of the spring. In conclusion, this experiment allowed me to observe both simple harmonic and damped harmonic motion experimentally. I successfully determined the spring constant and damping coefficient through my graphs. Also, my results closely matched to theoretical expectations. Thank you for watching my video.